Hello everyone, we are excited to present to you our innovative project, an autonomous ESP8266 mode-based IoT system for live ISS telemetry and cloud analytics. I'm Aina Aireena, and with me are my talented team members, Mawar Fasha, Aina Aireena, and Yasmin. In the next minutes, we will share with you the hardware components, the code that makes it work, and the demonstration.
So here are all the components that you'll need for this project. So the required components are ESP8266 mod with USB-C. Why did we choose this? Because it has a Wi-Fi module. And then we need SSD 1308 OLED display. We specifically choose 0.96 inch. And we need two LEDs. The first one is a data fetching indicator, and the second one is for overhead indicator. And then we need two 220 ohm resistor, a breadboard, multiple jumper wires, and also USB-C cable. And so for the connection, we will connect our OLED to ESP first. VCC go to 3.3 V in the positive rail. Ground go to ground in the negative rail. SCL go to D1, SDA go to D2. And for our LEDs, we have our first LED, the fetching indicator. For the LED positive leg, we'll connect it to a 220 ohm resistor, and then we'll connect it to D7. And for LED negative leg, we'll connect it to ground. And for the second LED, which is an overhead indicator, we'll connect the positive leg to 220 ohm, and then we'll connect it to D5. For the negative leg, we'll connect it to ground. For the power connection, we will connect the ESP8266 3.3V and ground pins to the breadboard power rail. And then we'll make sure that OLED and both LEDs and ESP all share common ground. And then now we're ready for the software. So these are the library that I've installed for our project. Now let's look at the code. I'll walk you through the most important sections only. So the first and most important, the Wi-Fi credential. We have to change this to match our Wi-Fi. And then our home location. If you want the overhead LED to work for your location, you can change these coordinates. And I've set ours to Sri Skandar Perak. It'll light up when the satellite is above our head. If you want to log your data to Google Sheets, we did this to log our entire data. We paste the app script URL here. Now let me show you the main function that make this work. So the first one is the void setup. It initializes Wi-Fi, OLED, and LEDs. And then we have void fetch ISS data. It gets ISS data from API every 60 seconds. And then we have boolean is ISS above home, which calculates distance to check if ISS is overhead. And next is void update overhead indicator. With the parameter of boolean is overhead, it turns the D5 LED on and off based on the distance. And then lastly is void update display. This switches between 4 display modes that we have every 10 seconds. So the mode being ISS live position, global map view, system statistic, and then lastly spinning globe animation. Display modes. So the display will automatically rotate between 4 modes every 10 seconds, and then we'll see all of them running shortly. So there's 4 modes. The first mode being ISS live position. It shows latitude, longitude, altitude, velocity, visibility, and also trend. And the second mode is global map view. It's a flat world map. It has ISS position marked. And mode 3 is system statistic. It checks data points that have been collected. It shows success and fail rates, and also uptime. And the last mode is a spinning globe. It shows 3D Earth animation with ISS track on the surface. So you can actually see where the ISS is when it's spinning. So the flow being ESP8266 device, it fetches ISS data every 60 seconds. And then from here, it sends HTTP post request to our Sheets script, act as a data receiver. It receives and stores data in Google Sheets. And then after that, from this sheet script, it stored the data in spreadsheet. And then after that, we move to dashboard script, which is our data processor. This dashboard script, it analyzes data and prepare for visualization. And then after that, it formatted and the data being ready, and then it goes to a dashboard visualization, charts and graph, and it creates real-time charts and statistic from the data that we have collected. Next is dashboard script. It acts as a data processor. So what it does is it analyzes collected data from the sheet, and then it provides statistics. Basically what it does is it receives ISS data from ESP8266, and then it saves it to Google Sheet. That's all. So for our ISS live orbital dashboard, we have mission snapshot panel, and this area provides quick information like total points or the data that we have collected. Right now it's 972. It shows how many data entries that have been collected. And then we also have success rate. It indicates how reliable the system is retrieving the data. So right now it's 100%, meaning all the data requests are successful. And then daylight share, the percentage of time that the ISS is currently in sunlight versus Earth shadow. And then we also have current altitude. It displays the ISS altitude in kilometers. And next, we also have altitude and velocity graph. And this blue line shows the ISS altitude over time. It naturally oscillates slightly due to orbital mechanics. And then the green line represents the ISS orbital velocity. And this dual axis graph, it helps us observe the relationship between altitude changes and also speed changes. Next, we have visibility status, and on the right, we have a pie chart that shows the ISS visibility status. The blue portion represents the percentage of time that the ISS is in daylight, and the orange portion represents the time that it is eclipsed or in Earth shadow. And next, we have a ground track map. This is the most important section. It is the ground track. It shows the ISS orbit projected onto Earth's surface. We have the curved blue line. It represents the orbital path of ISS on the Earth's surface. And then we also have the green marker. It indicates the current location of the ISS space station right now. And we also have the red marker. It represents the observer location, our location right now, which is Sri Iskandar Perak. And as the ISS orbits Earth every 90 minutes, the ground track shifts due to Earth's rotation. As we can see here, there's like 3 multiple lines. This visualization allows us to track when the ISS will be overhead for communication or our own observation. And last but not least, we have our recent telemetry, which shows our recent data that has been logged, and these are all the data that is collected. So that's all from us. Now you have a working ISS tracker, and check the project readme guide for more details, including the things that we have done. And me and my friends have worked on this project for quite some time, and we are happy that we finally finished this project. Thank you for watching.